Hi, in this video, we want to take a look at the multivariate normal distribution. Okay, so most of us are going to be very familiar with the bell curve Gaussian distribution, normal distribution. Now, normally when we talk about the normal distribution, we're talking about one variable at a time. Now, we're interested in the situation where I have multiple variables coming out at the same time, but there's a connection between each of them. They're not independent. Okay, well, if I'm in a situation where there's a particular higher dimension distribution of them that corresponds to the so that each marginal distribution individually, each dimension is normally distributed, and there's a connection between them in a very specific mathematical manner, then I have something called multivariate normal. Okay, so multivariate normal is the multiple variable version of the normal distribution. Now, anytime I'm working with data and it looks like I have correlated normal random variables, it's distinctly possible that multivariate normal could be a good choice for my situation. Now, when we talk about multivariate normal, we're talking about a finite number of dimensions. We're not worried about the case where I have infinitely many dimensions, which mathematically is possible, but for our use, for what we're talking about in data science, we really don't care at this point. Okay, so something I need to say is that if I have multiple dimensions of data and individually each one is normally distributed, that does not mean that cumulatively as a group it's multivariate normal. Multivariate normal is a more specific presentation. When we get into higher dimensions, things get very complicated. So just keep that in the back of your mind. Just know that that's a possibility. Now, something that comes out of multivariate normal is that zero correlation and independence end up being the same thing in this one special case. All right, so if I'm in a special situation that I'm working with multivariate normal and I see that I have zero correlation, then I know that I have independence between my variables. Now, that is just how it works out for this particular case. It is possible in other distributions that zero correlation is not the same as independence. That's very important. So just know that this is a very special case that comes up from being in this very specific situation. Now, if it ends up that multivariate normal is the right approach to modeling the situation that we're dealing with our data science problem, then this is awesome. This is great because this gives us a tool that's very powerful and we can get a lot of traction off of it. All right, so let's go ahead and take a look at univariate normal. So here, I'm just going over regular normal distribution, what we know and love, what we're familiar with. Well, we have a population mean, which is mu. We have a population variance, which is sigma squared. And we have this equation that we know and love. So, it's e to the power of -1/2 times x minus mean divided by standard deviation squared. And then I have a rescaling constant here to make sure that everything integrates to 1 when I integrate from -infinity to infinity. All right, so that's pretty familiar to a lot of people. If I'm talking about standard normal, mu is 0 and sigma squared is equal to 1. Okay, so in R, if I want to dig into univariate normal, well, I have d norm, I have p norm, I have q norm, and I have r norm to work with. So let's go ahead and just take a look just to kind of help us remember these functions. So if I want the density, I'm going to use d norm. Now, I have to specify what number I'm interested in for getting the density back. And I'm going to go ahead and just call that x here. And I'm going from -3 to 3. And I'm just going to take a bunch of values. I'm going to get the density value, the probability distribution function. And let's go ahead and plot it. So x are my values from -3 to 3. And the vertical axis is the probability distribution function for that particular value when I have standard normal. Okay, and so that's our bell curve, the one that we know and love, we're very familiar with. Now, if I want the cumulative distribution function, I'm going to go with p norm, p for probability. I specify my values, I specify my mean and my standard deviation, and then I just plot it. And we can see that here's our cumulative distribution function. So this gives me the probability of observing a value less than or equal to the particular value. So if I look at -1, here I can see that a little bit greater than 0.1 is the probability of observing a value less than or equal to -1. If I go up here from 0, I can see that the probability of seeing a value that's less than or equal to 0 is 0.5. All right, so we can see, the entire curve. Quantiles. So for quantiles, all I do is just pass in the values I want. So here, these are the probabilities. I want to know the x. If I plug it into the cumulative distribution function, or sorry, yeah, if I give a particular probability to the cumulative distribution function, I want to know the corresponding x. So previously we took an x and we got a probability. Now I want to go with a probability and get the x. So I want to go in the opposite direction. And you'll notice that this is an invertible function because it's always increasing. Okay, so here are the probabilities I'm interested in. I'm just going with the standard quantiles and specifying my distribution, and it gives me the values. All right, and you'll notice that it never actually reaches 0 and it never actually reaches 1, that we have to go out to plus or minus infinity for those values. Okay, now for random number generation, I'm going to use R norm, specify the number of observations that I want, specify the parameters of the normal distribution, and then I get the response back. Here I store it in a vector. I use V for vector. And here is my histogram. All right, looks like a bell curve. Okay, so that's the univariate version. That's just one dimension. Now let's go ahead and kick it up a notch. Now, if you start having trouble with this, if this feels uncomfortable, I recommend that you go back to the video that I made on bivariate normal. Bivariate normal, that video is talking about just 2 multivariate normal random variables. And so it's a little bit simpler, a little bit easier to work with. Here, I'm jumping straight into higher dimensions. For the examples we're going to look at 3 dimensions, just because that's really the limit that we can really start like doing scatter plots with. And so I stopped at 3. If we wanted to, potentially, we could have 100 dimensions in this if I just wanted to extend it. All right, so when I'm dealing with multivariate normal, I have multiple dimensions. And so for each dimension, I'm going to have a population average. I'm going to have a population variance also. But wait, there's more. I need to have the covariance between every pair of possible dimensions. So I need the covariance between dimension 1 and dimension 2. I need the covariance between dimension 1 and dimension 3. I need the covariance between dimension 2 and dimension 3, and so on and so forth. So for all possible pairs, I need a covariance parameter. Okay, so how we're going to code this, and this is the standard way, whether you're doing things in theory or if you're doing this inside like R or SAS or anything else, is that I'm going to have a vector for my averages, and then I'm going to have a symmetric matrix for my variance and covariances. Okay, so this is going to be a symmetric matrix. That's important. On the diagonal, I'm going to have the variances of each dimension. The first diagonal is a variance of the first dimension. The second diagonal is the variance of the second dimension, and so on. Now, when I look at my symmetric matrix, entry 1, 2 is the covariance between dimension 1, dimension 2. When I look at entry 2, 3, that's going to be the covariance between dimension 2, dimension 3, and so on. And so here I'm going to go ahead and generate some values. We're going to take a look at what the densities look like. And I'm going to go from -3 to 3. You'll notice that this time I dropped that length by a lot. All right, I'm dealing with higher dimensions. I'm going to be expanding things out. When I deal with higher dimensions, I can get a very large data set very quickly, and I'm not expanding out too much. So here, what I'm doing, for each dimension, I want the values from -3 to 3, and I want 20 values going from -3 to 3. Then what I'm going to do, I'm going to take all the possible x's, all the possible y's, all the possible z's, and I'm going to expand those out. So when I'm done, this is going to give me a data frame with 20 times 20 times 20 rows. So that's 8,000 rows. You can see that very quickly the size of this matrix will grow very rapidly. And so what I'm doing here, I'm trying to get the density for all these different possible values. Okay, so here I specify each individual value that I'm interested in for each dimension, and then I take all possible combinations of x, all combinations of y, all combinations of z. And that's why this ends up being 8,000 rows long when I started out with 20 times 20 times 20. All right, so I need to specify my average. Now here I'm just going with zeros just to make it easy, but I could change this to any value I'm interested in. And now I need my variance covariance matrix. Okay, so let's take a look at how this looks. What I'm doing here is that this is the variance of the first dimension, variance of the second dimension, variance of the third dimension. This is the covariance between the first and the second, first row, second column. That is the covariance between first dimension, second dimension. Now, covariance is directly related to correlation. All I have to do is divide by the two standard deviations for their dimensions, and I'll get covariance. But when we're dealing with higher dimensional normal, usually we deal with the covariance instead of the correlation matrix. Correlations are better for interpretation when I'm dealing with real world problems. Covariance is better for working with in theory, like I'm doing proofs and stuff like that. Covariance is the easier one to work with because I don't have that division aspect working out. Now here, we see that we have a covariance of 1 between dimension 2 and dimension 3, and a covariance of 0 between 1 and 3. And so you'll notice now that I have a symmetric matrix that if I reflect over the diagonal, I get the same value every single time. And the diagonal is here. Okay, so now let's go ahead and get the densities of my multivariate normal. All right, so here, this is a grid of values going from -3 to 3 in terms of x, y, and z, and all possible combinations of values I can get from x, all possible combinations of values I can get from y, all possible combinations of values I can get from z. So this is an 8,000 row data frame. What I'm going to do, I'm going to pass the value, the points I'm interested in the density, the population mean, my covariance matrix, and I'm going to put it into the density function. So here, this is the density of multivariate normal and the multivariate T and normal distribution package. This is by far the most used package in R for this purpose. There are plenty of packages in R that will tackle this, but this one is well established, well vetted, so it's the one I chose. All right, so now I want to go ahead and do a scatter plot for us to just to see what's going on. Now I have a whole bunch of different values for the density. This is a continuous range of values, and for the purpose of visualization, it's hard to see what's going on. So what I did, I used the cut number function to put all of my data points into one of 3 buckets by the value of the density. So what will happen is I have, after I run this code here, darker values will correspond to greater densities, lighter values will correspond to lower density values. And so I'll be able to see where are we more likely to get points in a higher dimensional sense. And so I'm using the gray palette to get the values. And so here I'm getting a color vector. And so here I'm defining what the colors are, and then I say what the names are, and then I use the index function, index utility in R to specify what each row's color should be. And so here, to my eyes, the code is intended to have 4 values, but I only see 3, white, gray, and darker gray. But we can see that here, in terms of X and Y, so here I'm only looking at 2 dimensions at a time with this. X and Y, here is where it's most likely to occur. Now X and Z, here is where it's most likely to occur. And here Y and Z is where it's most likely to occur. All right. And you'll notice that I have like a slope going on here in the overall shape. That is due to the fact that we have non-zero correlation. This, if I had, if I plotted on a perfect square going from -3 to 3 in both directions and it was square, then this would look like a circle because we have zero correlation. All right, so now let's take a look at multivariate random number generation. So what I'm going to do, once again, I'm going to go multivariate T normal package. I want random multivariate normal. I specify the number of observations I want. I specify the population mean as a vector, and I specify the covariance matrix. And here I specify the names just so it works out for me. And this, I wasn't sure what class I would get back from this, so I converted it to a data frame just to make sure. And here I use Plotly to plot the results. I'm going to do a 3-dimensional scatter plot. And this is actually an interactive plot. Markers is what's going to happen when I hover my mouse over an individual value. And we can just see that I'm matching X to X, Y to Y, Z to Z. So let's see what happens. So now notice that this is an interactive graph in my HTML file. And I can scroll over and I can see what each individual coordinates are. And I can move around. I could zoom in, zoom out. Now, 3-dimensional plots, they're so like alluring when you first get into data science, first get into mathematics. But when you work with them for a while, you realize that they really don't provide as much insight as you would hope. And so my recommendation is to skip 3-dimensional plots, but it's a very natural thing to want to do, so I went ahead and did it. All right, so now if I go through and I take histograms of the X coordinate, histogram of the Y coordinate, histogram of the Z coordinate, I'll see that in terms of just one dimension by itself, when I'm working with multivariate normal, in fact, I get a univariate normal when I look at just one dimension at a time. This is a very nice feature. And so if I go ahead and I plot just the X in a histogram, I'm going to get a bell curve. Now, there is a little bit here that's a little bit off, but remember, I did not take a very large sample because the higher dimension aspect. If I was to crank up the number of observations to, let's say 10,000, this will look a lot more like a bell curve. And the same is true of Y, and the same is true of Z. All right, so now let's go ahead and look at computing probabilities. Now remember, when I had cumulative distribution functions for one dimension, what was going on was that I just specified one value and it took that value to negative infinity and it did the computation for me. It gets more complicated in this situation because I'm in a higher dimensional situation. What I have to do is I have like rectangular boxes. I tell R what rectangular box I'm interested in, and it does the computations for me. So let's say I'm interested in the probability that x is between -1 and 3, y is between -4 and 4, and z is between 1 and 1. And then what I do, I pass the lesser value of each dimension, the greater value from each dimension in two separate vectors. So I put the lower value here. So this is the lower value of x, lower value of y, lower value of z. The upper vector is the upper value of x, upper value of y, upper value of z. And then I specify my population average, my covariances, and it will compute the probabilities for me. All right, so here it computed the probability that if I'm in multivariate normal with this mean vector and this covariance matrix, then the probability of being in the rectangular box defined by these three inequality statements is, about 0.36. Now, something about this is that this is a numerical approximation. It's not a perfect value. The computer can only be so accurate. And so this gives me an idea of how far off it is. So if I have to -5, if that's good enough for me, I'm good, I'm done. I don't need to crank up any parameters. Here, that's good enough for what I'm doing, so I leave it alone. I'm good, I'm happy. Now, quantiles in higher dimensions I'm not really satisfied with what we can do with it, what we can work with. Here it's Q multivariate norm in the same package, and I can specify, I just go ahead and run it, and I don't usually use it. Now with the t distribution, remember that if I'm using my sample to approximate my variances and my covariances, then I'm using the t distribution instead of the normal distribution. And so all I do to change that is instead of norm, I put t instead. Now something about this is that when I do this, I specify the normal distribution mean, the normal distribution covariance, and I specify the t degrees of freedom. And then I run through everything else like I did previously. And we can see if I was to go through and start looking at this and really comparing the two, we would see that we would have more spread out of a distribution than we did previously. The normal distribution will be more concentrated around like that, what would be the peak of the bell curve. Random number generation works the same way. But something that has a big difference is that now we don't have averages, because not all t distributions have averages in the situation. So if I'm working with degrees of freedom 1 at the t distribution, I have a centrality parameter. It's not an actual population mean, because the integral calculus doesn't make sense. The limit does not exist. And so here I specify the centrality parameter. So it's like, think median instead of mean. And then I specify my covariance matrix, specify my degrees of freedom, and then I run through everything exactly like I did previously. And once again, I get my three-dimensional scatter plot. And you'll notice that this is a little bit more spread out than what I had before. And so I'm seeing larger values coming out because there's greater variability in what's going on, because we have heavier tails on this distribution. Now, when I do the one-dimensional histograms, I see once again I get a t distribution, which is very nice. With larger value, if I had more observations, this would look more like the actual t distribution with 5 degrees of freedom. And everything works out pretty much the same for those rectangular regions like I talked about with the normal distribution. So if I want to figure out the probability of observing a point in a rectangular region, I just specify the lower values of every dimension, the upper values for each dimension, the central tendency. I specify my covariance matrix, and I specify my degrees of freedom, and it computes it for me. So now you'll notice that we have a lower probability here than what I had before. The reason for that is this is a more spread out distribution. And you'll notice that now I've lost some accuracy, that the error is a little bit greater. And so I need to be more mindful of this if error of a t-distribution would be a problem. And Quantiles works out to be the same way. I've never actually used it this way, but it's there. If you're interested in it, please read the help documentation. All right, well, that's all I've got for you. Take care and goodbye.